So let's take a look at the Hill cipher. The Hill cipher was developed by Lester Hill in the late 1920s. It was published in 1929. It's based on linear algebra and modular arithmetic. It's what's known as a polygraphic substitution cipher. So a substitution cipher, you're replacing letters or characters with other characters. And the polygraphic aspect is that the plaintext characters are encoded not single characters at a time, but in blocks of characters. So in the examples we will look at today, we will see encoding just 2 characters at a time, but we can encode more than 2 at once. And so as a result of the way the system is designed, a character is not necessarily encoded as the same ciphertext character each time it's encountered. It depends on what is around that character. The other characters around it will determine how it's encoded. So for the encoding, this is carried out numerically. So we will think of, for now, just the capital letters, A to Z, and number those 0 to 25, so the 26 letters. And so the way the process works is we begin with the plain text, and let's say we have the word linear. We convert that to numbers, so 11, 8, 13, 4, 0, and 17 is the numerical encoding of linear in this version. And so then we will separate that into equal dimensional vectors. So in our case, again, we're going to encode in blocks of 2. So we will separate this word, linear, into 3 two-dimensional vectors, just based on the numerical values of each of those. So the encoding then is carried out by matrix multiplication. So we have the number of available characters, and all the calculations are then mod n. So in our case, right now, we have 26 characters, so all of our calculations will be mod 26. If we had a different number of available characters, we would use the appropriate n. Sometimes there are some changes made and some kind of dummy characters created to make this number n be a prime number. That makes certain calculations easier going forward. But the encoding matrix that we create must be invertible mod n. So we'll look at that momentarily. So when we're encoding mod 26, let's say, we're going to select a matrix M. And so we're going to select a 2 by 2 matrix because we are going to encode blocks of 2. And so let's just make up a 2 by 2 matrix. So to encode, we will multiply the matrix by the vectors one at a time and do the calculations mod 26. So Li is 11, 8. We will multiply the matrix by that vector. It's the transpose of that vector because we need a column vector the way we're multiplying on the right. Do this calculation mod 26, and 11, 8 becomes 917, and 917 is the corresponds to the letters JR. So Li becomes JR. Do that for the next 2 and the 2 after that. And so doing all of these calculations mod 26, we see that linear, Linear, becomes JRFLFY. So each block of letters depends on the letter that's beside it in that corresponding block to determine what it becomes. So the encoding, we multiply by this matrix, and the transformation, the vector is transformed into another vector, and that vector then is converted back to letters. and that is our encoding process. So the decoding process, we need to be able to undo that. So to undo that transformation, we have our matrix M. We need to be able to invert that matrix to do the decoding. So we look at the determinant, but the determinant, again, we're looking at all of this mod 26. So the determinant in this case, the direct determinant would be negative 57, but mod 26, that becomes 21. So using the 2 by 2 formula for inverse of a matrix, we would have 1 over the determinant, and then we are applying the formula that says let's swap the location of the main diagonal entries and the off diagonal entries become negatives, but all of this calculation is mod 26, so we have to look at what's happening here. We need to see what is negative 9 mod 26, what is negative 11 mod 26, and what is 1 over 21 in this mod 26 universe. So to calculate 1 over 21, we can use Python. We're going to create a formula for the reciprocal. So we're going to give it n, which will be the 21, and the base in this case is 26, and we want to find out what 1 over 21 is. This is the number that when you multiply it by 21, you get 1 in the mod 26 universe. So what number can we multiply by 21 in order to get 1? And so we can kind of brute force our way through this. We can look at for I in range of the base. So just say start from 0 and go to 26. We could save ourselves a step and not start at 0. We could start at 1 instead, because 0 is never going to give us the value. But if n times I and then mod that base is 1, then we will just return that value. Because it turns out that if there is a reciprocal, if there is a number that you can multiply by 21 in order to get 1, then there will be only one of those of that number. So we won't have multiple multiplicative inverses here. And so in this particular case, we can then print this value. What is the reciprocal or the multiplicative inverse of 21 mod 26? And you run this and you will see what that multiplicative inverse is. So what happens is that 1 over 21 in this world is 5, and then negative 9 is 17, negative 11 is 15, and so the inverse of our matrix becomes this matrix 4, 23, 7, 9. Now that's not the inverse in the standard consideration. So we want to check this to see, is this really the inverse? If we take the original matrix M and multiply it by this M inverse, or the so-called M inverse, and again we could check both directions of this to make sure that the multiplication gives the identity, but we want to check, is this the identity? And so if we check this, here is the original matrix M, and here's our apparent M inverse. We do that calculation, 105, 260, 78, 261, but then when we do that calculation mod 26, we get the identity. So at least this is a right inverse. If we check the other side as well, this matrix is the inverse of the original matrix. So this transformation that is taking place in the mod 26 world, we can undo that by using this inverse matrix here. So here's the inverse matrix. We have the encoded message now, JR, FL, FY. We take those two-dimensional vectors and do the multiplication. Multiply m inverse by 9, 17. Again, this is the transpose of that vector. And if we do that calculation mod 26, you can check, and we do get 11.8, which is the Li that we were hoping to be able to get back. Each of these calculations, you want to do this, work this out, and make sure that you believe this. We transform this back into NE, and here, multiplying by the inverse, transform this back into AR. And so JRFLFY becomes linear when we decode using this corresponding inverse matrix in the mod 26 universe. So in general, we do not have to do all these calculations mod 26. We can modify that according to the number of characters that we want to encode. But the encoding matrix that we use must be invertible mod n, whatever the n that we choose. So how do we tell whether the matrix is invertible? So the determinant must be non-zero mod n, just as in the typical case when the determinant must be non-zero. But that is not enough. Now again, there are other ways other than the determinant being non-zero to tell, but this is at least one approach that we can use to determine whether the matrix has an inverse. The determinant not only has to be non-zero mod n, but it has to have a multiplicative inverse mod n, because we need to look at 1 over the determinant. So that multiplicative inverse has to exist, and if it doesn't exist, then there will be, again, no inverse. But another way to tell is that the determinant must be non-zero mod p for every factor p of n. Now we're typically in this kind of setting, p you think of as being a prime. We just want to make sure that for every factor of the n that we're choosing, that determinant has to be non-zero mod that factor. So the idea is that we can tell whether a matrix is going to be invertible as we're creating it, especially in a small case like a 2x2. It's easy to tell, oh, I can't choose these values because that will give me we've picked 3 of them. Let's say we have 3 of the numbers. What can the 4th one be? Or we pick 2 of them. What can the other 2 be? We want to make sure that that encoding matrix is invertible. If it's not invertible, we can encode, but we won't be able to decode. And then we can use larger matrices if we want, so in order to encode larger blocks. So if we want to encode 3 characters together, or 4 characters together, or 5 or 10, if we're encoding a very large set of text, then we might want to encode large blocks at once. There is overhead that goes with that. The larger the block, then the more work there is in terms of the calculation, in terms of determining what the inverse of the matrix is, and so on. But we're able to encode and decode so long as the matrix that we select has an inverse mod the n that we choose. Again, n is separate from the block size. The block size is determined by how big our matrix is. The n is in terms of how many characters we are encoding. Now this method was kind of a beginning of a use of linear algebra and a use of other tools in cryptography. By itself, it's not a very secure system. It's easy to break. But as part of other more advanced systems in the almost 100 years since it was developed, it has laid the groundwork for a lot of other systems that exist. So this idea is an application of techniques of linear algebra in a way that we might not typically think of. Typically, when we're thinking of linear algebra, we're thinking of solving equations, or we're thinking of geometric kinds of things. And in this situation, the transformations are characters converted to numbers, transformed, so a different kind of transformation than we tend to think of in this kind of setting. So as usual, feel free to ask questions in the comments, by email, or on Discord, and have a great day.